My name is Luke VanderHart. I'm going to be talking today about the ReactJS landscape. So I'm sure a lot of you are at least familiar with the name React right now. You're familiar with OM. This is something that's got a lot of attention recently, and I believe well-deserved attention. The purpose of this talk is to talk to you about why it's gotten attention, why that attention is well-deserved, and what your options are when you're using it from Clojure. React itself is a JavaScript library. So there's actually 3 ClojureScript libraries that wrap OM in various ways, and they have very different philosophies and opinions. The goal of this talk is to give a quick overview of each, to give you a flavor of what each is about, what the individual opinions of each one is, what some of the design decisions behind them were, and to hopefully give you the ammunition you need to decide between these 3 libraries when you're developing JavaScript UI in ClojureScript. I'm not going to, unfortunately, have time to go in depth on how to use each of these. There's just not time for that in a 40-minute talk. But the goal is to give you a flavor and to talk about some of their similarities and their differences. So first we have to ask the question, what is React? Why should we be interested in this library? What is it? And according to its website, it is a JavaScript library for building user interfaces. Well, that sounds useful. But if you've been in the space at all, you know here are some other libraries for building user interfaces that have exactly the same description. In fact, there's another painting that comes to mind when I think about the JavaScript landscape, and it's this one. I really have no idea what's going on here at all. So a better question that we can ask ourselves is, why React? Why should we care about React? What distinguishes it from the crowd of all the other libraries out there? So this is a very, very terse but correct statement about React. React utilizes a virtual DOM to performantly enable immediate mode style updates to user interfaces in a browser environment. Well, that's a mouthful. That was the shortest expression of React's value proposition that I could come up with, but definitely needs some unpacking. In plain English, React lets you write user interfaces as if you were not working with something slow and mutable. It lets you pretend that you're working with something fast and functional, which to me is a pretty big win. But let's unpack those 2 aspects we mentioned before, the virtual DOM and immediate mode style rendering. So what's the difference between the DOM and the virtual DOM? Well, pretty much the virtual DOM is better, faster, stronger in every way, unshackled by the constraints of reality. That's actually not a bad analogy. Every time you do something to the real DOM, you have to reach into the browser and mutate this state, which is an expensive operation. The browser's doing a lot. It's got to render. It's got to adhere to this massive spec. And so every time you update the DOM in the browser, you're doing a lot of work. The virtual DOM, on the other hand, is really lightweight Java objects. You have no constraints on how fast you can manipulate the virtual DOM other than the speed of your JavaScript engine. And JavaScript engines are getting really fast. So typically the virtual DOM is so much faster than the regular DOM that if we can work with it, it's a big win. Also, immediate mode rendering. So this is how I learned to program. Dijkstra would probably say this is why I am still crippled as a programmer and can't understand Haskell. But this is how I learned to program. You actually specify all your pixels, and then you just iterate over every pixel on the screen and write the pixel that you want to be there. And there's a certain elegance to this approach because there's only one code path. I don't have to worry about what was there before. I don't worry about any kind of transformation. I have my screen, I have my data that I want to write, and I just stick it right to the screen. I can disregard the previous state. This makes my code vastly simpler. You don't have to worry about what you're overwriting. You just have to write what you want to write. And so this is how React works as well. So this is the fundamental model of React's interaction path. You have your code. Your code renders virtual DOM. React handles the reconciliation, and React has something called the component model that gives some structure and helps you arbitrate how your code generates a virtual DOM. Then React has this thing called reconciliation, or React DOM diffing, wherein React calculates the minimal set of diffs to take your virtual DOM and commit it to the real DOM. But it can do that in a very, very efficient way because if it knows the whole structure of the virtual DOM and it knows the structure of the real DOM, it can make as few changes as possible to reconcile and bring the virtual DOM into alignment with what you want. So that's quite powerful. And then, of course, from the real DOM, you get events, right? And your events eventually call back into your code, which then has the option of re-rendering more virtual DOM, which can be re-reconciled, and so on and so forth. So this is the React model, but it's also going to look pretty familiar as Flux to those of you who have looked into that. And Flux is really more of a way of doing things than it is a particular library. And these are both libraries from Facebook, by the way. So what is the virtual DOM? Well, it's composed of React elements, which are element nodes. They mirror pretty much the normal DOM nodes we think of. You have divs and paragraphs and spans and all that good stuff. And a React component is a custom element node that you write in the virtual DOM. And components are really what is central to React. When we think about the act of writing a program in React, what we're really doing is we're defining components. So components are custom elements. You write the component specification or the component class. Instances of that component become React elements. They live in the virtual DOM, and React actually utilizes them when it's generating the DOM, and even to some extent when it's doing deltas with the real DOM. It utilizes the extra information that you can give it in the components to enable be a little bit more intelligent about the way it renders. So if your real DOM or your virtual DOM looks something like this, you're sticking some components in there. You'll see you have the same actual element nodes. The actual structure that will get rendered to the real DOM is the same, but we've stuck in some components. And what the components do is they give us control. They give us additional control over how a component renders. They give us encapsulation. So the general structure of a component, and I realize I'm going over this very, very quickly. You're not intended to be able to use it just from this talk. This should hopefully give you an idea, is a component has properties, which are the definition of the component. They're what make it what it is. They are set by whatever built it, set at construction time, typically, that specify how this component should look and should be and should feel. Components also have private state that they can update themselves. And typically, state is only updated from within the component itself. Only the member functions of the component, so to speak, would update the state. And then we also have a few different functions we care about. Render. Render is the process of generating virtual DOM underneath this component. So components are responsible for managing their own children, typically. So this is great for providing encapsulation. If I say I want a blog post on my screen, then I can just use this blog post component, and I don't have to worry at that point what the children of that are. The component is responsible for managing its own children. And that's built using the render function. The other function we care about is should component update. Should component update is pretty important, and it gets even more important as we'll see, because it looks at properties, it looks at state, it looks at any changes to the properties or state, and it calculates whether we even need to do anything. So this is a means of getting a lot of efficiency, because if nothing's changed, then we don't need to re-render the DOM, and we can actually just ignore that whole subtree of the DOM underneath this component, which gives us a lot of efficiency. There's also lifecycle hooks. I'm not going to talk too much about those in this presentation, but they're just ways of saying, oh, after we render, do this, before we render, do that, before we reconcile to the DOM, do this and that, etc. One note I will make, because this is kind of confusing terminology in the React docs. React component render is the process of generating a virtual DOM. The top level render method, which takes a React element and a DOM container, is the process of applying the virtual DOM to the real DOM. So those are two uses of the word render that mean completely different things. One is generate the virtual DOM. The other is apply the virtual DOM to the real DOM. So I just wanted to make a note, keep those two things separate. So why do we care about ReactJS and ClojureScript? That was a whirlwind overview of some of the quick benefits of React. Well, we care about it because they just go together really well. There are other things that go together really well. And in this case, what goes together really well is immutable objects and should component update. This is what lets React from ClojureScript a lot of times be even faster than React from JavaScript. Because in JavaScript, if you want to test if two objects are equal, you have to do a deep walk of each object to test if it's the same, because somebody may have mutated a little leaf node of it at any point. The immutable objects, you can just check identity, or check equality. And ClojureScript has very good support for fast equality checks on immutable objects. And so we can very, very quickly eliminate vast swathes of our virtual DOM from needing to even calculate the virtual DOM or needing to render it. And this gets us a lot of efficiency. That's one reason that ClojureScript and React go very well together. The second reason is a functional style of programming. So React enables a view of the world that goes something like this. The view is a function of the data. And this is the feature that is closest to my heart. If you really only remember one slide from this presentation or one statement, this is the biggest value proposition to me to programming in a functional way and to using React to do so, is it lets you think about the world this way. And we're going to see that more as we explore some of these other libraries. So next, we're going to talk about the three libraries that are available, wrapping React for ClojureScript. There is Ohm. We know about Ohm. There is Reagent, which is quite nice. I've been using it a little bit more recently. And then there is Quiescent, which I actually wrote, and I'll talk about some of my motivations for doing that and how it differs from the other two. But first, I want to show you an example program that I wrote that actually demonstrates all three of these. So give me a second to flip over. All right, so this is a game, tic-tac-toe. But I was doing tic-tac-toe as an example, and it turned out it's pretty boring. So instead, I actually went onto Wikipedia to look at the rules, and I was like, is there any way to make it more interesting? And it turns out there is. Quantum tic-tac-toe. So instead of just playing in one square, you create a superposition of plays. And it's formally equivalent to playing multiple games of tic-tac-toe at once. Each player has to create an entanglement between two squares. And you just proceed playing like that. Until you create a cycle of entanglements. And then you have to collapse the superposition, which forces classical interpretation of the game. So you can read the rules on Wikipedia. It's kind of cool. It's very complicated to play. It's hard to wrap your head around. But it's fun, and especially if you're playing with any physicists. It was actually first published in a physics journal as a teaching tool, and there's a number of features of actual quantum mechanics that it demonstrates quite well. So it actually might help you get a little bit more of an intuitive understanding of how quantum superposition and collapse works. So go check it out. The reason I mention it here is that there is a repository on GitHub down there at the bottom. I just made it public that has this game written in, it's got one backend, and then it's got a front end written in every single one of the libraries we're talking about today. So some good examples, and that's where my examples are taken from. So anyway, continuing on with that, the code snippets we're going to see will come from that example program. So first, a couple disclaimers talking about this. I'm very biased. I have strong enough opinions that I actually put a lot of work in and wrote my own library on this stuff. So I'm going to talk about the other two. I'm going to try to do them justice. I do have a lot of respect for them. But I do have certain opinions that can't help but leaking through. So just keep in mind, I am the author of Quiescent, and I'm not going to back down from being in that place. I'm also going to compare these libraries based on emphasis, not based on capability. A lot of these libraries are really flexible. All of them have shortcuts that allow you to do things that they don't support as part of their normal workflow. So I'm not going to, like, if I say, like, Ohm wants to do things this way, well, you know there's going to be somebody say, no, you can actually use this function and this function, and then implement that protocol, and then you can make it work that way. Sure. I'm going to talk about what the libraries emphasize, kind of what, where the path that they lead you down, as opposed to, you know, just the sheer amount of things that they can do. The other disclaimer is that things move really fast. If you follow, you know, the library authors on Twitter, you'll see that there's new versions of this stuff coming out all the time. A lot of what I'm going to say about Ohm, for example, is probably obsolete already. But this was all accurate as of 2 weeks ago when I was writing this presentation. So, you know, keep that in mind. So we're going to ask a number of questions about each of these libraries. We're going to ask, what opinions does the library have? And we're going to talk specifically about application state. Where does the state live, and how is it updated? To me, that's one of the most fascinating aspects of these libraries, and one of the big discriminating features that we really want to talk about. And then, of course, how do you engage with the library? What are the APIs? What does it actually feel like? So the first one we're going to talk about is Ohm. Ohm really was responsible for bringing React to the public consciousness even. Even React itself owes a lot of its current popularity to Ohm and some of the evangelism that people were able to do around that, particularly David Nolan. And Ohm is really about giving you the full power of React. So there's a number of opinions that Ohm has. You want to stay pretty close to React's component model. They like the component model. You want to operate in that way. You want to define components, which are kind of like objects. You want the full power of React. You don't want to eliminate anything that React gives you, and you want to expose that all. But you do want to work with immutable data, is a key tenet of Ohm as well. And we do want to get the benefits, the performance and the conceptual functional programming benefits of working with immutable data. And also, if you've watched David's talks, we do want the good parts of object-oriented programming. So Ohm has a lot of features that are geared towards giving you things like encapsulation, modularity, reuse, writing components that can be reused in a variety of different contexts. And this is Ohm's goals. So state. Cursors. Cursors are strange beasts. They're fun. Cursors are how Ohm manages its application state. They have an underlying atom. So in Clojure terminology, they are identity types. They arbitrate updates to the application state. Whenever you want to update your application state, you do so through the cursor, using the transact function, actually. They provide local access to the application state value for encapsulation. So you can update the state in a localized way without knowing what your broader context is. And this gives you encapsulation. It lets you write components that don't have to know where they are from the top level. Cursors also have the interesting property that sometimes they can behave as pure values. You can use them just like you would a Clojure map or a vector. If you're in a render context, they actually behave just like values. You can still transact to them, but you can also do things like assoc to them or call get on them, just like you would any other Clojure map. Another key feature of Ohm is you've got two kinds of state to think about. You've got your application state, which is your top-level cursor or cursors. This is kind of global to your application and lives at the top level and drives top-down rendering. Whenever the application state changes, of course, it forces a re-render. But then you've also got component state. And component state is directly maps to React's concept of component local state. This is private state that is available to a component that can update independently. If you update a component state, that will trigger a re-render. But it doesn't have anything to do with the application state. So it's for local transient things that you don't want to escape the context of an individual component. So using Ohm, I'm not going to take the time to explain this code in great detail. But this is kind of what defining a component in Ohm looks like. You write a function that reifies any number of protocols. The one protocol you have to implement is iRender, or iRenderState, if it's a stateful component. And that's it's a function, or it's a method on your component object, which we're reifying here, that returns some virtual DOM. And then you can build up some virtual DOM. DOM-div is a function that builds up a virtual DOM. You can specify attributes. And then you can use onBuild to nest other components. So I have another component called board. And I can build, so here I'm rendering out the game, rendering a div called play area, rendering a board. So this is kind of what writing an Ohm component looks like. Then you got to set a render route. So this is actually my main function. And the way to do it is you get an atom that is going to become your root application state. Wants you to use a single atom as your root application state. And you say root, and you give it a component. You give it the atom that is your state, and then you actually specify a location in the real DOM that it binds to. And from then on, updates happen automatically. If I update that game state atom, it will update the screen without me having to do anything else. This establishes a live reactive process where it continually updates. And then when I want to update something, so here, for example, I have a little a table cell, and if I want to click on it, I can set up a click handler, and when I get the click, I can actually transact my game cursor. All updates to Ohm application state have to go through the cursor. Every component gets a reference to the cursor, and I can simply transact to it. So This function is actually into my domain model for the quantum tic-tac-toe game. And it, as in a good functional game, each game state is a function of the previous game state, which means I can just call transact, which has similar semantics to Clojure's swap, and invoke my play function on that, and off it goes. So that's kind of the really high-level gist of Ohm. There's a lot more. Obviously, you should read the documentation or go look at talks on it to actually use it. But hopefully this gives you a little flavor of it. I will give a few cautions about using Ohm and things that we've seen. Use it only for front-end rendering. We actually came onto a project one time trying to clean it up a little bit. And what we found is they used a classic model view component architecture, which is great. And they had their views written in Ohm components. Every view object was an Ohm component. Well, so far so good. That makes sense. The problem was that their models were also Ohm components. And their controllers were also Ohm components. That's not really what Ohm is designed for. The best way to use Ohm is to keep it as the view layer only. Every component should directly represent something on the screen. It should be an actual widget that renders on the screen. It's tempting, particularly if you come from an object-oriented background like I did, when you're writing Clojure, to the minute you get something that looks like an object, and even if there are great parts to the, if you're using the good parts of object-oriented programming, there's a great temptation to start using it for everything again and to start structuring your application that way. And I believe that's a temptation that should be resisted. The other thing is keep components simple. Ohm exposes a lot of awesome functionality to you. There's lifecycle methods, there's component local state. Don't use that stuff unless you have to. Every time you do that, it makes these objects more complicated, more stateful, and before you know it, you've got a big object-oriented system with a lot of really heavy stateful objects that all talk directly to each other. That's going to be a mess. Keep them light, keep them simple, use them just to render data out. Don't use state unless you have to. And you will avoid writing code that looks like that, which it is possible to do in Ohm. It's possible not to, certainly, but that tends to be one of the failure modes of writing an application in Ohm, is to get something that looks like that. All right, next library we're going to talk about, Reagent. Reagent is very cool. I have been liking it more the more I've used it. And it's got some really neat features that it's just very clean and very clever in ways I really appreciate. So what are Reagent's opinions? Well, you want things to be clean and easy. And when I say easy here, I don't mean it disparagingly, as some people in the Clojure world say, well, that's easy, not simple. No, this is easy in the good way. It's easy to use, and it's not incredibly complicated either, or it's not complected either. And you still want the hard things to be possible, but within this simpler paradigm. So it's actually a way of thinking about how can we get the same capability that React gives, but simplify the APIs a little bit. Rather than kind of having one-to-one with all the features of React, like Ohm does, we're going to back off and say, well, what are some simplifying abstractions we can make? So the key part, feature that Reagent gives you is special atoms. Reagent defines its own atom type that you use throughout, and this is where the magic comes in. I got to say, I love Reagent's name, because not only in modern chemistry is it something that facilitates a reaction, given that we're talking about reactive programming in React, that's clever, but in medieval alchemy, reagent was something that helped you transmute one element to another element, one type of atom to another type of atom. And it does indeed use a different kind of atom. I don't know, I am appreciative of that naming effort. So reactive atoms are what Reagent gives you. They have the same API as a standard atom. The difference is that they track dereferences. Whenever you dereference a reactive atom, it does some magic. It establishes a link across time. Rather than dereferencing being a one-time event, it now establishes a dependency and said, the code that I just rendered by derefing that atom now has a causal dependency on that atom. So if that atom ever changes, that means that I need to go re-update this component as well. So if you dereference an atom once while you're rendering, excuse me, then in the future, updates to the atom will automatically cause a re-render of that component. So the dereference, the act of dereferencing, establishes a reactive link, which is kind of cool. So it gives you structures like this. So in Ohm, and as we'll see in Quiescent, your application typically looks like this. You've got one atom that's your main application state, and then you have a bunch of components that all build from each other, and the first one gets the value of the atom, and then they all kind of drive top-down building. But Reagent lets you structure your application like this, if you want to, where this component depends on these two atoms, and this component depends on that atom, and this component depends on that atom. And so we've kind of unified the concepts of global application state and local component state just based on how many people have references to the atom. If you have an atom that only this component uses, well, that atom is effectively that local component state. And if you have an atom that kind of drives the rendering from the top down, then that atom acts more like a global application state, which is pretty cool. It uses the same idiom for multiple concerns, which I do appreciate. And it does end up simplifying code substantially. So what does it look like to use Reagent? Well, you define your application state as an atom. Again, it's a reagent atom. It's not a closure atom. And then you can write your components as render functions. Now, you'll notice this is very, very lightweight compared to what we saw with Ohm. And that's because Reagent does a lot for you. It implicitly creates components. And it uses a hiccup-style markup syntax, vectors with keywords that represent the DOM nodes. So that all you have to do is write render functions. And then, for example, if I return a nested component, Reagent automatically looks at that and says, well, that's a function. So I'm going to assume it's the render function of a component. And behind the scenes, it actually creates the React component for you. So you aren't working with the React component model directly. Instead, you just write these functions. And it feels more like writing a functional program. And then anywhere you want, you can dereference a reactive atom, which means that whenever that changes, it'll re-render this component on the screen, which is kind of cool. And it's similar to Ohm. You set up a render route. You render. You got to give it a little fragment of markup. So this is actually markup here. It's a div, or sorry, it's a it renders a single component. I have a component called screen. And then it puts it on this, you give it an actual real DOM element to anchor to. And again, this render sets up a dynamic process such that it renders that component. You'll notice I don't actually care about my application state here. The components dereference it themselves. But this sets up the reactivity. So whenever any of my reactive atoms anywhere in that render process change, it will force an update of that component and of all the components underneath. So pretty elegant, pretty nice. I encourage you to go take a closer look at it and at its documentation. Some cautions about Reagent. Don't use too many atoms. This feature of reactivity is really nice, but if you're not careful, what you might end up doing is writing a program that effectively has a large number of global stateful variables, which each atom really is, right? So this is a powerful feature, but use it judiciously. I would recommend either use one or two as your top-level application state holders, and then render top-down and just pull out values from that, or have an atom that is scoped to a single component, a single instance of a component even, and use that as the state holder for that component. So use it to emulate component state. Don't have a bunch of top-level global things that you're dereferencing all over the place willy-nilly, because that's going to lead to a more messy program. And one that has the same pitfalls that we're all aware of in programs that have a lot of stateful places. Clojure-like state. Localize your state into as few places as possible. And that definitely holds true here. Have as few atoms as you can get by with. The other caution is don't deref your atoms in every single component. So this one's a little bit trickier to understand, but if I have a top-level application state atom, it's possible to deref that in every component in my application. But that's not actually necessary. What you can do is deref that in your top-level component and then pass the values from that onto the children. And that's actually much, much more efficient, because that means that the children will only render when they need to. Remember, each component has a should component update based on the values that it gets passed. Well, if it's dereferencing an atom and the atom changes, then every component has to re-render every time the atom changes. Whereas if we are careful and only dereference the atom in the top level component and then pass values to our child components. Because reagent components are not forced to deref an atom. They can also just take values, be passed values to render. Then you're going to get some more efficiency there. So that's just a caution. Don't deref more often than you have to. And that's Reagent. I like it. You should definitely check it out. There's been some good experience reports I've seen of people using that. Next, we're going to talk about Quiescent. I got to get a drink, sorry. So, Quiescent is a library that I wrote. Not because I thought the other libraries were not good, they are. But there are a number of opinions that are a little bit different from the other libraries, which is you like functional value-oriented programming. Cursors and reactive atoms are all kind of addressing the problem of how do we hold state. And Quiescent is saying, well, what if we didn't worry about holding state? What if we just worried about programming with values? And you want to do your own app state management. You don't want your rendering library to be concerned with how you manage your state. Maybe I want to use an atom, but maybe I don't want to use an atom. Well, with the other two options, you're kind of forced to use an atom because that's the idiom that they use. Quiescent, you can store your state however you want. Quiescent also has an interesting opinion. Component local state is bad. We don't want a bunch of state living in a bunch of components all over the place. And this is a controversial opinion. It makes certain things, granted, a little harder to write. But it also means that we're adhering closer to the idiom is the program is the view is a function of the state. All rendering is top-down. So when you render a Quiescent application, you have your application state, you re-render that into a view. You have your state, re-render it into a view. Your components have no activity that's happening automatically. There's no reactivity happening except from that top level. I want to apply my view function to my state and get a new view. And that's why it's called Quiescent, because it doesn't do anything reactively. Nothing happens unless you explicitly tell it to. It doesn't give you state. It just doesn't unless you work with values. So interestingly, it occupies kind of a different place in the whole system. In Ohm and Reagent, they kind of manage this whole process of having your application state and getting the values, the data out of your state, and then turning that into components, and then rendering that to the DOM. That whole process is handled. With Quiescent, it really only handles the middle process, the process of taking your data and turning it into components. And then it also gives you some tools for writing it to the DOM. But what it explicitly does not do is know or care where these values came from. Right? You could create the values every time. You could store them in a mutable object. You could store them in an atom. You could store them in a database and request them from the server new on every request. Doesn't care. Gives you flexibility there. And we talked about the view being a function of the data. That's true of all of these libraries, but Quiescent tries to make that a little bit more explicit. This is the primary API of Quiescent, the render function. We'll see that more. This is actually exactly this form. Take my widget, my component. It's a function of the data that becomes my view, and then I can just render the view to the screen. So it's really trying to make this the central idiom of it. So what does defining a component look like? Well, you've got this macro. It's a thin wrapper around a function. You can also write a function to define a component. You give it a name. You give it some arguments. And you have then similar to Ohm, you build up virtual DOM components. It's a little bit different. You just call child components as functions. You call their constructors like a function. You can pass it values through. You can pass closure maps as attribute maps. Interesting thing about Quiescent is the first value that you pass in to a component is the value, the immutable value upon which its rendering is based. Any subsequent arguments that you pass, it will not use that as a driver for whether the component needs to re-render or not. So here we go and create a screen. It's built on a game. This game is a value. It's just a standard closure map. And then it knows if it sees this, if you call screen again and you pass it exactly the same game, it just doesn't need to re-render because that under the hood is handled for you by React comparing with should component update to see, oh, my driving value doesn't need to cause an update, or it does. If the game atom, for example, changes, that will not cause it to re-render. It's just useful for passing around like communication channels or things that are going to remain the same for the lifetime of your app are useful for additional things. So again, go read the documentation for that. We don't have time to talk about it in incredible detail here. Here's what rendering looks like. Now, interestingly, you'll notice the quiescent render function doesn't establish a persistent rendering process. This is a key difference. It renders it once, which means if I want my application to render more than once, I have to call render multiple times. Right? So quiescent gives you control over when you render. And so a common idiom, and this is what I do in tic-tac-toe, is I just render on every frame. And rendering is actually efficient enough if nothing's changed that this is a totally reasonable thing to do. I'm calling quiescent's render function 60 times a second, and it just works because React is smart enough to know that if my game state, which I'm dereffing there, hasn't actually changed, it goes no further. It doesn't actually re-render anything. But I can call the render function on as if I don't care whether the whole application had rendered and was already ready or whether I have an empty DOM. All I do is I just call render on my component, on my state, and it just makes it true. And that brings us back to the immediate mode rendering. I don't care what was there before. I just want to render my data, my value, onto the screen. And then, of course, I recursively call it, so I render multiple times. So, what are some cautions about Quiescent? Well, it's a little bit lower level than the other libraries. It doesn't give you as much. You have to write your own render loop, for one thing. You have to come up with a way of managing state. So you got to choose good higher level idioms. You got to build on top of it a little bit more and know what you're doing a little bit more. And you may have to abandon it at some point. And by abandon, I don't mean stop using Quiescent. I mean use either some other library or just go write some raw React components. All of these libraries, by the way, combine reasonably well. So you can have a whole tree of Quiescent components and then a little React component that you write using JavaScript API at the bottom level. And it's sometimes necessary to do that with Quiescent. You can't do everything through Quiescent. Quiescent deliberately blocks off certain features of React from you in the name of functional purity, because React is not itself functionally pure. It has state all over the place. But say you really, really, really need state, and you just can't think of a way to do it without using state. You may have to abandon this. That is something I should mention about React is, or about Quiescent too, is it does kind of have a philosophy that if it matters to your application at all, it should be in the top level state. So even like the toggle state of an individual low level component, that's not encapsulated. That's actually just part of your UI state, which should just live in the top level application state. Another library I want to mention, I don't have time to show examples, is Q. I'm basically just giving it a shout out. All the other things we saw let you build React components by calling functions and composing virtual DOM as data or as function calls. Q lets you use existing HTML as a template in the style of InLive, for those of you who have done that. So if you actually want to work with designers or work with somebody, actually want to work with markup that looks like markup, Q is the way to go. It's usable from Reagent and Quiescent. It's pretty easy to plug into all three of those. So give that a shot. So what's next? We've talked about these three libraries. These are all good paths forward. Based on your personality, based on your goals of the project, I could see using any of these three on a project, depending on what you like. If you like object-oriented style programming, you want to keep the good parts of that. You want really rich power. You think about Ohm. If you want something that's just simple, you can get it going, it's easy. Think about Reagent. If you want hardcore functional programming, think about Quiescent. But we have three good paths forward. And I actually kind of consider the problem of taking values and rendering them to the DOM to be sort of a solved problem. For the first time in my life, I actually enjoy browser programming using one of these libraries. So that's pretty cool. But we're not done. We have to worry about state management. And that's something that some of these libraries address a little bit, but I still think we have a long way to go. Because in an application, ultimately, you have some sort of persistent state. You have a database, right? And then you have some sort of application state, your domain model, the state of the application itself. And then you have your UI state. And then, of course, you need to render your UI state into the DOM. And so this part, your UI state rendering to the DOM, that's what these libraries address. But they don't address any of these upstream concerns. And there's a lot of question marks. What are these? Are they tuple stores? Are they atoms? Are they flat data? Are they deeply nested tree data? What about the channels between them? Are they core async channels? Are they over a network? If they're over a network, are we replicating state using some sort of replication technique? Or are we using RESTful HTTP requests? Are we using, the process of mapping back and forth between your logical model and your UI model, is that something that you want to do using functional programming, or do you want to do it using logic programming? There's a lot of cool things you can do with logic programming, rules, core logic that we could use to map between these. So I don't have any good answers here. This is just something to think about going forward, and I would encourage all of you to think about it. I see this as the next big problem that I would love to see some good solutions and some good libraries out there in the ClojureScript UI space to be used in combination with these other 3 libraries that we have to build some pretty effective patterns for building user interfaces in Clojure and ClojureScript. And I think it's an exciting prospect, and there's a lot of interesting territory to explore. Thank you very much. That's all I have.